Scheduling. An event planner has to juggle many workers' completely different tasks, some of which must be completed before others can begin. For example, the banquet tables would need to be arranged in the room before the catering staff could begin setting out silverware. The event planner has to carefully schedule things so that everything gets done in a reasonable amount of time. The problem of scheduling is fairly universal. Contractors need to schedule workers and subcontractors to build a house as quickly as possible. A magazine needs to schedule writers, editors, photographers, typesetters, and others so that an issue can be completed on time. Getting started. To begin thinking about scheduling, let us consider an auto shop that is converting a car from gas to electric. A number of steps are involved. A time estimate for each task is given. Task 1, remove engine and gas parts. Task 2, steam clean the inside of the car. Task 3, buy an electric motor and speed controller. Task 4, construct the part that connects the motor to the car's transmission. Task 5, construct battery racks. Task 6, install the motor. Task 7, install the speed controller. Task 8, install the battery racks. Task 9, wire the electricity. Some tasks have to be completed before others. We certainly can't install the new motor before removing the old engine. There are some tasks, however, that can be worked on simultaneously by two different people, like constructing the battery racks and installing the motor. To help us visualize the ordering of tasks, we will create a digraph. A digraph is a graphical representation of a set of tasks in which tasks are represented with dots called vertices and arrows between vertices are used to show ordering. For example, this digraph shows that task 1, notated for T sub 1 for compactness, needs to be completed before task 2. The number in parentheses after the task name is the time required for the task. Example 1. A complete digraph for our car conversion would look like this. The time it takes to complete this job will partially depend upon how many people are working on the project. Processors. In scheduling jargon, the workers completing the task are called processors. While in this example, the processors are humans, in some situations, the processors are computers, robots, or other machines. For simplicity, we are going to make the very big assumptions that every processor can do every task, that they all would take the same time to complete it, and that only one processor can work on a task at a time. Finishing time. The finishing time is how long it will take to complete all the tasks. The finishing time will depend upon the number of processors and the specific schedule. If we had only one processor working on this task, it is easy to determine the finishing time. Just add up the individual times. We assume one person can't work on two tasks at the same time. Ignore things like drying times during which someone can work on another task. Scheduling with one processor or a possible schedule would look like this, with a finishing time of 10 days. In this schedule, all the ordering requirements are met. This is certainly not the only possible schedule for one processor, but no other schedule could complete the job in less time. Because of this is an optimal schedule with optimal finishing time. There's nothing better. Optimal schedule. An optimal schedule is the schedule with the shortest possible finishing time. For two processors, things become more interesting. For small digraphs like this, we probably could fiddle around and guess and check a pretty good schedule. Here would be a possibility. With two processors, the finishing time was reduced to 5.5 days. What was processor 2 doing during the last day? Nothing, because there were no tasks for the processor to do. This is called idle time. Idle time. Idle time is time in the schedule when there are no tasks available for the processor to work on, so they sit in idle. Is this schedule optimal? Could it have been completed in 5 days? Because every other task had to be completed before task 9 could start, there would be no way that both processors could be busy during task 9, so it is not possible to create a shorter schedule. So how long will it take if we use 3 processors? About 10/3 equals 3.33 days. Again, we will guess and check a schedule. With 3 processors, the job still took 4.5 days. It is a little harder to tell whether this schedule is optimal. However, it might be helpful to notice that since tasks 1, 2, 6, and 9 have to be completed sequentially, there is no way that this job can be completed in less than 2 plus 0.5 plus 0.5 plus 1 equals 4 days, regardless of the number of processors. 4 days is, for this diagram, the absolute minimum time to complete the job, called the critical time. Critical time. The critical time is the absolute minimum time to complete the job, regardless of the number of processors working on the task. Critical time can be determined by looking at the longest sequence of tasks in the diagram called the critical path. Adding an algorithm. Up until now, we have been creating schedules by guess and check, which works well enough for small schedules, but would not work well with dozens or hundreds of tasks. To create a more procedural approach, we might begin by somehow creating a priority list. Once we have a priority list, we can begin scheduling using that list and the list processing algorithm. Priority list. A priority list is a list of tasks given in the order in which we desire them to be completed. The list processing algorithm turns a priority list into a schedule. List processing algorithm. 1. On the diagram or priority list, circle all tasks that are ready, meaning that all prerequisite tasks have been completed. 2. Assign to each available processor in order the first ready task. Mark the task as in progress, perhaps by putting a single line through the task. 3. Move forward in time until a task is completed. Mark the task as completed, perhaps by crossing out the task. If any new tasks become ready, mark them as such. 4. Repeat until all tasks have been scheduled. Example 2. Using our diagram from above, schedule it using the priority list below. T sub 1, T sub 3, T sub 4, T sub 5, T sub 6, T sub 7, T sub 8, T sub 2, T sub 9. Time 0, mark ready task. Priority list. We assign the first task, T sub 1, to the first processor, P sub 1, and the second ready task, T sub 3, to the second processor. Making those assignments, we mark those tasks as in progress. Priority list. Schedule up to here. We jump to the time when the next task completes, which is at time 2. Time 2. Both processors complete their task. We mark those tasks as complete, with task 1 complete. Task 2 becomes ready. Priority list. We assign the next ready task on the list, T sub 4 to P sub 1 and T sub 5 to P sub 2. Priority list. Time 3. Processor 1 has completed T sub 4. Completing T sub 4 does not make any other tasks ready. Note that all the rest require that T sub 2 be completed first. Priority list. Since the next 3 tasks are not yet ready, we assign the next ready task, T sub 2 to P sub 1. Priority list. Time 3.5. Processor 1 has completed T sub 2. Completing T sub 2 causes T sub 6 and T sub 7 to become ready. We assign T sub 6 to P sub 1. Priority list. Time 4. Both processors complete their task. The completion of T sub 5 allows T sub 8 to become ready. We assign T sub 7 to P sub 1 and T sub 8 to P sub 2. Priority list. Time 4.5. Both processors complete their task. T sub 9 becomes ready and is assigned to P sub 1. There is no ready task for P sub 2 to work on, so P sub 2 idles. Priority list. With the last task completed, we have completed schedule, with finishing time 5.5 days. It is important to note that the list processing algorithm itself does not influence the resulting schedule. The schedule is completely determined by the priority list followed. The list processing, while doable by hand, could just as easily be executed by a computer. The interesting part of scheduling, then, is how to choose a priority list that will create the best possible schedule. Choosing a priority list. We will explore 2 algorithms for selecting a priority list. Decreasing time algorithm. The decreasing time algorithm takes the approach of trying to get the very long task out of the way as soon as possible by putting them first on the priority list. Decreasing time algorithm. Create the priority list by listing the task in order from longest completion time to shortest completion time. Example 3. Consider the scheduling problem represented by the diagram below. Create a priority list using the decreasing time list algorithm. Then use it to schedule for 2 processors using the list processing algorithm. To use the decreasing time list algorithm, we create our priority list by listing the task in order from longest task time to shortest task time. If there is a tie, we will list the task with smaller task number first, not for any good reason, but just for consistency. For this diagram, the decreasing time algorithm would create a priority list. Once we have the priority list, we can create the schedule using the list processing algorithm. With 2 processors, we'd get time 0. We identify ready task and assign T sub 3 to P sub 1 and T sub 1 to P sub 2. Time 6. P sub 2 completes T sub 1. No new tasks become ready, so T sub 4 is assigned to P sub 2. Time 7. P sub 1 completes T sub 3. No new tasks become ready, so T sub 2 is assigned to P sub 1. Time 10. Both processors complete their tasks. T sub 6 becomes ready and is assigned to P sub 1. No other tasks are ready, so P sub 2 idles. Time 20. With T sub 6 complete, T sub 5 and T sub 7 become ready and are assigned to P sub 1 and P sub 2, respectively. Time 24. P sub 2 completes T sub 7. No new items become ready, so P sub 2 idles. Time 25. P sub 1 completes T sub 5. T sub 8 and T sub 9 become ready and are assigned. Time 27. T sub 9 is completed. No items ready, so P sub 2 idles. Time 28. T sub 8 is completed. T sub 10 becomes ready and is assigned to P sub 1. This is our completed schedule with a finishing time of 35. Using the decreasing time algorithm, the priority list led to a schedule with a finishing time of 35. Is this good? It certainly looks like there was a lot of idle time in this schedule. To get some idea how good or bad the schedule is, we could compute the critical time, the minimum time to complete the job. To find this, we look for the sequence of tasks with the highest total completion time. For this diagram, that sequence would appear to be T sub 2, T sub 6, T sub 5, T sub 8, T sub 10, with total sequence time of 28. From this, we can conclude that our schedule isn't horrible, but there is a possibility that a better schedule exists. Critical path algorithm. The sequence of tasks in the diagram is called a path. In the previous example, we saw that the critical path dictates the minimum completion time for a schedule. Perhaps, then, it would make sense to consider the critical path when creating our schedule. For example, in the last schedule, the processors began working on tasks 1 and 3 because they were longer tasks. But starting on task 2 earlier would have allowed work to begin on the long task 6 earlier. The critical path algorithm allows you to create a priority list based on idea of critical paths. Critical path algorithm, version 1. 1. Find the critical path. 2. The first task in the critical path gets added to the priority list. 3. Remove that task from the digraph. 4. Repeat, finding the new critical path with the revised digraph. Example 4. The original digraph from example 3 has critical path T sub 2, T sub 6, T sub 5, T sub 8, T sub 10, so T sub 2 gets added first to the priority list. Removing T sub 2 from the digraph, it now looks like the critical path, longest path in the remaining digraph is now T sub 6, T sub 5, T sub 8, T sub 10, so T sub 6 is added to the priority list and removed. Now there are two paths with the same longest length, T sub 1, T sub 5, T sub 8, T sub 10, and T sub 3, T sub 7, T sub 8, T sub 10. We can add T sub 1 to the priority list, or T sub 3. We usually add the one with smaller item number and remove it and continue the process. I'm sure you can imagine that searching for the critical path every time you remove a task from the digraph will get really tiring, especially for a large digraph. In practice, the critical path algorithm is implementing by first working from the end backwards. This is called the backflow algorithm. Backflow algorithm. 1. Introduce an in vertex and assign it a time of 0, shown in brackets. 2. Move backwards to every vertex that has an arrow to the end and assign it a critical time. 3. From each of those vertices, move backwards and assign those vertices critical times. Notice that the critical time for the earlier vertex will be that task time plus the critical time for the later vertex. Example, consider this segment of digraph. In this case, if T sub 2 has already been determined to have a critical time of 10, then T sub 1 will have a critical time of 5 plus 10 equals 15. If you have already assigned a critical time to a vertex, replace it only if the new time is larger. Example, in the digraph below, T sub 1 should be labeled with a critical time of 16, since it is the longer of 5 plus 10 and 5 plus 11. 4. Repeat until all vertices are labeled with their critical times. Once you have completed the backflow algorithm, you can easily create the critical path priority list by using the critical times you just found. Critical path algorithm version 2. 1. Apply the backflow algorithm to the digraph. 2. Create the priority list by listing the task in order from longest critical time to shortest critical time. This version of the critical path algorithm will usually be the easier to implement.